Great. So this week we were talking about power transmission. Basically, it's just a lot of stuff having to do with taking energy from one source and moving it to wherever you need it to be. So, for example, if you've got a motor and you want to run a wheel, that's what we're talking about. And so we're going to be using the words torque and speed kind of a lot in the next few slides here. And as I go, I'll explain what they mean. But generally, we're going to be using gears, belts, or chains. And again, I'm going to go through each of these a little more in depth. So when we're talking about the source, we're usually using motors. It could look like this one. It's usually got some kind of a body and then a shaft that rotates, and then some wires that electrical has to worry about. It takes the electrical power and converts it into mechanical. It's pretty basic stuff. Most of you have probably already worked with motors plenty a bit before. So when we're looking at motors and you've got a website open and you're looking at this motor that you might want to buy, or you're looking at one that you already have and you're trying to figure out how, you're going to be looking at a lot of different numbers. And so we'll talk about a little more of them. So you've got kV, and as you can see here, it's a measure of how many rotations per minute a motor makes when just 1 volt is applied. So when you have a higher kV, you've got a higher spin rate, which means lower torque. So speed and torque are inversely related. So when one goes up, the other one goes down. So to think about speed and torque, you can think about speed. If you're hammering a nail into a wall, speed is how often you hit that hammer. Torque would be how hard you're hitting the nail. So sometimes you need a lot of force. Maybe that's what you need. Like if it's a really hard material, you'd need more force or torque. If it's an easy material and you want to get it done fast, then you'd want a higher speed. And so depending on what you need, that's what you can look at for kV. So power is how fast work is being done, and P equals IV if you've taken like a physics course having to do with like electromagnetism. This comes up a lot. P equals IV. If you have a higher power, then it's faster spin up time. And when I say spin up time, that would be how long it would take to get from 0 rotations per minute to the max. So, if you have more power, then it can speed up faster. Speaking of current, we've got the max current and stall current. So again, if you've taken any kind of circuits course before, or you've learned anything about circuits, you'll know that motors would act as a resistor. So even if it's part of the system and not doing anything, it's going to be drawing some kind of current. So that's what stall current would be. If it's not running, it's still drawing a little bit of current. However, when it's running a lot, it's going to draw more current. So these are other things to look at that you might want to consider. You might want to throw these numbers over to the electrical subteam and say, hey, is this okay? Can our battery take this? Can our system take this? And same thing with max voltage. So this more has to do with the battery that you're using, and also is related to power. As we said before, P equals IV. And even though you're looking at a max voltage, we're probably not going to be wanting to run the motor at the max voltage the whole time, because that's how you burn out a motor real fast. For a useful website, if you guys know Young, he recommended this one. Basically, it's got a lot of basic information about motors, kind of a lot of review of what I just talked about. And it's got a neat calculator that you can use to help figure out the specs. So I'm going to go ahead and send this link in the chat for anyone who might want to bookmark it or something like that. Continuing on, this is something what you'd be looking at. So generally, you're going to see a lot of different numbers with a lot of different titles. And so it takes some time to like look through and get used to finding all this different stuff. And it never hurts to ask an electrical member. Yeah, it never hurts to ask people on electrical team because they're used to dealing with this stuff, and they know like what's probably a good range of numbers. So yeah, as I said before, sometimes you need torque for heavier things, which means less voltage, or you need more voltage for things you want to get done faster. It really depends on what you want to get done. So that's enough about motors. Let's talk about gears. Gears, it's if you want, well, you guys know what gears are for. They're really great for high torque because of their nature. They're really tough and the teeth mesh together really well. If you need a lot of torque put in, it's a really great way to transfer that torque. When we talk about belts later, then you'll see why belts slip, and we'll talk about that later. Again, torque and speed are inverses. So it has a lot of the torque and speed stuff with gears has to do with pitch diameters and the gear ratio. So we're going to talk about the gear ratio in this slide. So when you got two gears next to each other, they could be the same speed, or sorry, the same size, or you could have a little gear and a big gear. And so you'll have a driving gear and the driven gear. And so the higher the ratio, the lower the speed. What that means is if you have a little gear driving a big gear, that means that you're going for torque. If you have a big gear driving a little gear, you're going for speed. And this ratio is really important if you're trying to calculate how many teeth you want to use. Again, these are stuff you'd want to check with an older member to make sure this is what's going to work for you guys. But generally, just knowing the properties of the ratio are enough to help get you started. So we've got several different gear types. You're probably used to seeing spur gears all the time. You've got parallel shafts, and so like if the motor is connected to the small gear, it would be driving this big gear, which would be driving a shaft. That would, and since it's small to big, you'd be putting a lot of torque into this second shaft. And usually these ratios aren't that dramatic. They're really easy. They're really efficient. Spur gears work. Bevel gears are a little more complex. You've got perpendicular shafts. So if they're like making kind of an L shape here. Again, these are really high efficiency, less common, but they still work really great. Then you've got the worm gear and the worm type. I don't think I've ever seen these like used on a robot, just me personally, but if anyone else has, that's really cool. These are not as common at all. Generally, the worm itself has only one tooth. What happens is this gear rotates, which will then rotate the shaft. So it's another perpendicular shaft transmission like the bevel gears. But the way it works is because this is effectively one tooth, the ratio between the worm and the worm gear is going to be huge. And let's see here, cannot drive worm with worm gear. I misspoke. The worm itself is what's driving. So that means if you've got the little number on top and the big number being driven, again, that's for torque. All right. Then we've got my personal favorite is the planetary gearbox. So what you're looking at right here is you've got these three blue gears are stuck in between this big inner gear. So you see it has teeth on the inside and then a tiny sun gear. And basically, these create huge ratios due to their nature And they're actually used in a lot of practical applications like car transmissions, wind turbines, stuff like that. So when you stick a bunch of these together, where you'd connect these planetary gears with a sun gear of another set, then you can create these exponential ratios that are super effective at driving torque. Another way to put a system together is to just have spur gears in series. And I've got a really great slide or a really great video example that shows how this works. So I'm not going to play this whole thing because it's 10 minutes, but I'm going to send a link in the chat so that you can watch it later. This is really fascinating stuff. So this person has just a lot of Lego gears. And you see, so this is the motor, and it's spinning this tiny gear really fast, which as he's increasing the number of teeth, they're turning slower, but they're putting out more torque. And when you get your gear ratios perfectly, then you can end up with a predictable rotation. So now you can see that this person's using a worm gear. So you can see how that works. And these little dials that are spinning are just kind of references. So now what this person has effectively done is created a clock. And so now we've got an inner gear, or with inner teeth. And it's still technically a worm gear because it's being driven by in effect, I think what this guy ends up doing is creating gear ratios up to a Google, which is kind of insane. And it's never actually going to finish a single rotation. But yeah, this is effectively kind of a not exactly, but a version of a planetary gear set. So you'll see that when he spins the center, all the others rotate around. And so I'm going to stop it here. Again, I'd highly encourage you guys to watch this at some point. Ooh. I know I did. All right, so that's enough about gears. Do you guys have any questions before I move on? All right. So next is belts. You've seen plenty of belts. Essentially, we're using pulleys to transmit power. So again, it's like gears, or it's like spur gears where our shafts are parallel. And but instead of using gears, we're using this flat, or we're using this belt. So depending on the ratio of the diameters, so like gears depended on the number of teeth, and technically also the diameter. So this is the same kind of relationship. And so we're going to be talking about flat belts, V-belts, and timing belts. So flat belts, you've probably seen these a bunch. They're super thin, and they're super efficient. And see here, when it says pulleys must be aligned on the same plane, that means that even though the shafts are parallel, you still have to have the other side in the same mid plane as this first pulley. So if they're not aligned perfectly right, then what's going to end up happening is this belt is just going to slip right off. It can be run on an entirely flat surface. So because it's flat, it's pretty easy to use. And so when it's talking about making the belt fit into a shallow inset in the metal, what it means is that maybe the lip of this pulley would be slightly raised so that when creep happens, when the belt starts to kind of slide over to the side a little bit, it can still be kept within the bounds of the pulley, and it won't just fly off. So V-belt, looking at this picture, it's kind of hard to tell that it's different from a flat belt, but it's got thickness to it. In this diagram, you'll see it's got kind of a trapezoidal cross section. And so because it's not quite as flat, it has to do with more friction. It's less efficient than flat belts. And when you try to run it at high speeds, it's not as effective. However, because of these sidewalls and like the fact that it's being constrained pretty heavily, as opposed to the flat belts where you might have a little ridge, you don't need nearly as much tension to keep it in place. So if I go back to this flat belt, it's got to be pretty tight between these two pulleys. If I had it loose at all, then and it had slack in the middle, then it wouldn't work nearly as well. But when I've got this V-belt, then it's much easier, or you don't need to worry about the tension as much. So it's called a V-belt because of this trapezoidal shape, not because we've got this kind of triangle. So this system is actually pretty similar to what we're using in steering for robo racing. Basically, we've got a V-belt, and then this third pulley is attached to a like a sliding mount, so that we can loosen it by sliding it forward and taking off the belt. And then when we put it back on, we can slide it back until it has enough tension. And so that's something to keep in mind, is how are you going to mount all these pulleys so that you can easily either change them out or anything like that. So you might recognize a V-belt because it's part of your week 2 CAD guide. This is what you use the sweep function for. And so you can see that you had made that kind of trapezoidal cross section, and then you swept it in a slot loop. It's pretty neat. It's a practical application of what you did. And then finally, we've got timing belts. So as you can see, they've got these ridges in it, kind of like teeth of a gear. And these are great for low speeds. You've got no slip. With flat belts, you could think, if it was going at a really high speed and it stopped, just kind of slip until it brought it to a stop. However, if this gear stopped, then this whole belt would also stop instantaneously. So yeah, it works really great with gears or pulleys. And it's really great when you need to stay exact with your belts. So like I said, it's really easy to measure when you've got these specific teeth in it. But the downside of the no slip idea is that you've got something it have something called hard stopping. So if you're in BattleBots, you'll be able to think that if you have your weapon spinning really fast and it hits another robot, this weapon's going to stop. And what's going to happen to what's driving that weapon? So the power transmission to that weapon is also going to have to stop. And so what would happen with a flat belt is it would be able to take the power that's still coming from the motor, because the motor would still be providing power even though the actual weapon itself is stopped. But the belt itself would be able to slip without having to kind of force things or jam things. But if we're using a timing belt, then because one end is stopped, it would have to stop the motor end. And if the motor in, but it can't, that's really bad. We don't want that at all. So again, having no slip, great for lower speeds, great if you're not going to have it hard stop at all. But if you are, then we should probably stick to something that's going to slip. And so chains are similar to belts, or similar to timing belts, but not quite the same. So again, we've got parallel shafts. And again, it depends on torque and speed, depends on the diameters. So that's information that you can carry through basically this whole this whole presentation. But we can talk about the pros and cons of belts versus chains. So belts, they're way more flexible. They're made of a material that can be made taut, and then you can tighten it a little bit more. And then, as I had explained earlier, they don't put as much stress on the motor because they can slip. But chains don't stretch out. So like with belts, one really good example is in a bandsaw. You've got that really tall box on top of the bandsaw. And if you open it up, you're going to find a belt on a bunch of pulleys. And that belt is the saw itself. And so sometimes it'll stretch just a little bit and you'll have to retighten it. But chains, you don't have to do that. They're not affected by high heat. It's not much, we didn't really talk about it before, but if you think about it, when you've got chains that are made of metal that can handle high heat, then it won't get warped. It won't be negatively affected by it. And then greater tensile strength. If you think about that flat belt, you would think if you pulled on it too tight, it would probably snap, which would be pretty bad if anyone was standing next to it. But chains, you can pull on them real hard before they're ever going to think about breaking. So you'd probably break whatever's pulling before you broke the chain. And then disadvantages. Easier to snap or cut through. Again, so if you think about that flat belt, if it got a hole in the middle of it and you keep running it, it's eventually going to just kind of snap. And again, we need to keep high tension, so we need some kind of adjustment system. Like with steering, how they have that the sliding third pulley. It's a really good mechanism, but they still needed to keep that in mind. And then chains, we talked plenty about slip, and it weighs more. So if you really need a lightweight thing, if you need like a 3-pound robot, it's something to keep in mind. So that's enough about belts. Does anyone have any questions before we move on? I'm going through this relatively fast, but I think we can handle it. All right. So let's talk about shafts. The main thing I want to focus on in this slide is this picture right here. We've got 3 different directions when we're talking about shafts. We've got axial, which is along the axis of the shaft. You've got radial, which is directly out from the axis, and then tangential. So if you've got the axis, it's the direction it turns in. So if I had, I'll use the typical example of a bug standing on a record, a vinyl record that's spinning around. It would be moving in a tangential direction. And we're going to be talking about what different shafts will constrain what different direction. So usually things will constrain things radially. That's probably like the most common thing, is if you constrain one shaft to something else, they won't be able to move out from each other. So we're not gonna be talking about that so much. And then because of friction, usually one will take care of the other. So we'll talk about that. So last week, we had almost this exact same picture, and so we're going to be talking about these a little more. You might need multiple methods to fully constrain a shaft, and that's okay. This you might recognize as like a lock on one of those Razor scooters. Good times. So the first one we're going to talk about is interlocking shafts. So you can see from the title, it's called a D shaft or D slot. You can see because it has this kind of D shape, where if you're trying to turn this shaft, it has to turn this slot, or yeah, it has to turn the slot as well. So as you can see, if I turn it, since they have to turn together, it's constrained tangentially. And then it's also constrained axially because there should be a ton of friction between each of the sides of this D shaft. So because we can have some pretty strong materials, then this works great. However, because of this weird cut, it can make manufacturing hard. So usually when you're dealing with shafts, we like to use the lathe because it cuts in a circular shape. So when you're trying to think about it cutting this straight line, it makes it a little more difficult to manufacture and keep it precise. Set screws, we talked about them last week. I talked about them with my door handle that comes off because the set screw is too loose. Again, because of friction, what's going to end up happening is the set screw places enough pressure so that the shaft can't move axially, and if it's tight enough, it also can't move tangentially. So if you spin the shaft, it will also spin whatever this collar is. So this is technically a collar with a set screw in it. And it works if it's under low loads. So, door handles work great. I'm not putting a ton of pressure on door handles. But if I used enough force, I'd probably be able to work past this friction of the tiny little screw. Then we've got retaining rings. This is one thing that doesn't restrict tangentially. As you can see in this picture, basically it just it wraps around this shaft, and then you just pinch it shut. And it requires a little groove so that it can restrict the axial direction, and yet it can still spin around. So as you can see, since it's on the other side of this gear, it's like sticking a nut. It would be like if this was a bolt and we stuck a nut on it so that it wouldn't be able to move away from this gear. It's the same idea, except because the cylinder, or because the shaft is completely flat and there's no thread on it, we can use a retaining ring. And then last one is the shaft collar. So like I said, with if you had like a Razor scooter as a kid, this is the part that would be that would prevent your steering handle from like collapsing into the scooter. Again, it's an axial kind of thing. So depending on the interior, you'd be able to rotate within this shaft collar, but like this hexagonal shape, you probably wouldn't be able to rotate within it. If you could, then you've probably got too small of a shaft. So unlike the retaining ring, which needs the groove, you don't need any kind of modification on the shaft to use the shaft collar. You can just clamp it down. And so some use this clamp that'll pull, or you'd have something similar to a set screw where if you tighten it down, it'll pinch this shut. Oh, and this is the last one. These are keys. So this restricts tangentially. So if you want things to be able to slide in and out, but you don't want them, but you want them to rotate together, this is what you've got. So I'm actually dealing with a project using this, which is kind of cool. You've got this key seat, which is essentially just like a rectangular prism cut into it. Like if you took a rectangle and extrude cut into this shaft, then you end up with a key seat and a keyway on the other side. Usually we just call them keyways. And then this key is just kind of a block of metal. And what's really great about this block of metal is that all the stress is going to concentrate here, which means that if anything's going to break, it's going to be the key. And that's good because keys are really easy to replace. Like I said, they're basically just blocks of metal that you can buy pretty cheap from McMaster. And you just have to cut out the length you need, and that's it. However, the manufacturing complexity as a whole is added because sometimes if you wanted to make your own, this would be difficult. Usually these come as stock parts though. So keys are neat. And you've got a bunch of different kinds. So you're probably going to see a lot of these key slots like this. But you might also see any variation of these. And then the keys themselves can also be any variation of these. It really depends on what kind of parts you have. Generally, we just find what we need in the shop, and then if we don't have the appropriate key, then we can get it. We don't usually design with this in mind. But you can. So we're going to look a little more just at the practical application of these retaining shafts using this 30-pound BattleBots horizontal spinner. So essentially, this is the weapon for Valkyrie. And if you take a cross-section wireframe look, and you can do this within Inventor, where you can cut into a view and then also make it a wireframe so you can see each individual line. So this would be a keyway, where instead of the key being just a block of metal, it would be a set screw. And as you can see, if this is rotating and something's going to break, it would be the set screw. And those are easy to replace. It's much easier to replace than anything else that we'd have to manufacture again. And then in the bottom, it's harder to tell, but this is actually a D shaft cut. And so that would make it constrained axially, tangentially. And same thing here. If this set screw is tight enough, it would be axial and tangential. So talking about stress, about how we, if we're going to concentrate stress in one part, it would be like the set screw or something like that. We've got puzzle fits. And I know we've been talking about BattleBots a lot today, but that's because there's a ton of application with BattleBots. They've got a lot of mechanical focus. And so puzzle fits are really great because, as you can see, there are essentially rectangular cuts on these sides, and then the inverse is cut into the other sides of the box that it's connecting to. And so if you think about building, like, I guess a frame, you could do puzzle fits, which are really not easy to make, but they assemble pretty tightly. Or you could just slap the sides of wood together and just screw it in. And so if you slap the sides of woods together, then the strength of that material, or the strength of that bond, depends on the screws. But when you do this puzzle fit, it depends way more on the strength of the material, which makes them really cool looking and really useful. So does anyone have any questions before we get to the Kahoot? If not, then you can go ahead and go to kahoot.it and we can get started. All right. All right, so we got 12 people. Oh, monkey, great. Reject humanity. Very nice. 3 people are really thinking hard about their name. All right, I'm going to give it 1 more minute, and then I'm going to get started. It's too bad you can't hear this music. It's really groovy. I always go with, I can't remember who recommended that. It might have been Keaton. Maybe it's Tomas.
Dude, Kahoot music is the bomb.
I know, but the funk one, you've got so many different options.
Dude, imagine not going for 8-bit, man.
8-bit. Not a fan.
How dare you?
But we'll get started. All right. Shaft is spinning. Gear is not. What are we lacking? All right. Good job. Remember, axial is if the shaft can move in and out along the axis. All right. Frowny face and the lead. Gear on the left is driving. Is it for speed or torque? Awesome. That's good to see. I know, I kind of beat it into the ground, but it's useful to know. Gear on the left has 7 teeth. Gear on the right has 21. What is the gear ratio? Oh, I may have not covered this. It was on the slide. I just didn't talk about it. All right. Well, I'm glad it was between these two. But yes, so I'll go back so that you can see it. So the driv or the driving diameter, driving number of teeth is on the bottom. So it'd be 21/7. Ooh, frowny face for frowny face. Kind of power transmission is theoretically best to run this BattleBots weapon, which is run at very high speed. All right, flat belts, yes. Timing belts, we don't want to run at high speed because of hard stopping. And then V-belts are just not as good at high speed. All right, true or false? Disadvantage of belts, they transmit any torque applied directly to the motor. We're talking about belts in general. So it would be true if we're talking about timing belts, but usually when we talk about belts, we're talking about either flat or V belts. So their advantage is that they can slip, which means that the torque doesn't get applied back to the motor. All right, what does it mean if you have a high KV? All right, this is tough. peak RPM or getting to peak RPM faster would be a function of power. So more power would get to peak RPM faster. What actually changes the RPM would be the kV. Gear system allows for crazy high or low gear ratios. And we're talking like crazy high. All right. Yeah, worm gearboxes, they can go pretty high, but planetary has a beat. All right, what is not a property of a chain? All right. Again, like what is it? Timing belts, because they don't slip, it would if one end stopped, it would transmit the torque right back to the motor, which is bad. All right. Oh, frowny face coming back. Stall current is the highest current the motor will draw at the max RPM. So stall current would be the current when the motor's not running at all. Last question. Which two shaft retainers prevent tangential movement? Ooh, I knew green would throw some people off. So the shaft collar on its own, you would be looking at this thing right here without the set screw. So without the set screw, then you would still be able to have tangential movement. But the D shaft and key would definitely prevent that tangential movement. So let's see who came out on top. All right. 9 out of 10, another 9 out of 10 with Paul. All right. Kirsa, congratulations. This is your second win, I believe. All right, well, good job, guys. That is the end of that Kahoot. And so now we've got, let's see here. So now it's guide time. So I'm going to go ahead and send this link into the chat. And so the way this is going to work is the same as last week, where if you want to stick around and watch me skim through it real fast and just talk about the tough parts, then I'm going to go ahead and do that. However, let's see here, if you feel like you've got it under control, or you have something to do, or if you just want to watch the step-by-step video later, then you can go ahead and step off the call. Speaking of the step-by-step videos, we do have them available. I send out the playlist link each week. I'll show you guys what it looks like. So if you're looking at our main RoboJackets training page, you just scroll all the way to the bottom and you got the mechanical training playlists. So for this week, if you view full playlist, it's the week 4 CAD guide. I walk step by step through each slide of the CAD guide. And then this is also where the recorded lectures go. So if you're really struggling on stuff and you don't want to ask us for whatever reason, this is your best friend. So I'm going to get started with this CAD guide. I'll see some of you next week. All right. So this week 4 CAD guide, it's a review for features. So if you're new to CAD, this is great. If you want to brush back up on it, this is also great. This used to actually be the week 2 advanced CAD guide, but I decided to move it to its own week because I thought it was important. So we're going to be making basically a steering wheel. It looks like this. This knob would be if you wanted to be able to spin the wheel with one hand, like on a forklift. Then you've got some more views here. But don't worry, we've got actual numbers on the next slides. So this first sketch, pretty simple, pretty self-explanatory. The tough part might be creating this arc here, but you have all the information that you need in order to create it. Then once you rotate or revolve that part around, then we're going to create a sweep. So basically we're going to take the plane, the mid plane of this. This would be the center of the wheel, and you're going to create a singular path. And again, these arcs might give you a little bit of an issue, but if you use the correct tangential constraints, it's definitely doable. Then once you do that, you can make the circle as your profile. And you're also going to make the second plane so that you can sweep to it. And now we're going to, like you can make work planes, you can also make work axes. So that's what we're going to do. And so we'll take this sweep pattern and we'll revolve it around that axis. Then you're going to create a mid plane with this arm, and you'll be able to revolve around this whole wheel part. And so now we can add in the little extra details. So we're going to be able to use some chamfers and fillets. If you just follow the images on the slides, it's pretty easy. Be careful with your fillets. If you misclick the wrong edge, then you're going to have to go back and like start over. So just be careful about where you're clicking, what you're selecting. So we're going to be creating fillets with the different radii. It'll end up looking really nice. And now for the spinner. So the spinner is probably the toughest part of all this. So you're going to create a work plane and make a sketch on it. That's pretty easy. And then you're going to create a symmetrical extrusion. So instead of going straight up or straight down, it's going to go both. And then you're going to fill it to the sides so it gets this like dual teardrop shape. And this is probably the hardest part, is creating this plane. You're not going to need any dimensions, but what you'll notice is it's going to be cut this into 2 symmetrical halves. Yeah, I would recommend if you're struggling with this part, the video will explain it, I think. I'm pretty sure. I made the video. But once you have that, from there, you just have to create another sketch that you'll end up revolving. And then you could just add a full round fillet onto it. And at the very end, you can highlight the whole part, set it to be aluminum 6061. And then when you open up the properties, you'll be able to actually see the mass, center of gravity, the moments of inertia. It's really neat stuff. Oh, you can find density. So that if you actually made this part in real life out of aluminum 6061, you'd be able to predict exactly what kind of properties it would have. So if you do it correctly, you should end up with numbers. If they aren't these numbers exactly, then you'll end up with something very close to them. So yeah, that's the CAD guide. If you have any questions, feel free to send messages on Slack. We've got the Piazza. No one's ever used it, but it's always open. And yeah, I'm always happy to help. So just let me know. Are there any questions, or else I'm going to stop the recording here, and you guys can head off, and I'll see you next week.